So with this in mind, we can look at the MDP's idea of what a Bellman equation looks like. And this will be the Bellman expectation equation, where we're going to take a look at the value function for a particular policy and for all of the states that we have in our system, and say, again, this is the expected value of the immediate rewards that we would get when leaving that state by a particular action, okay? With the future information, right? So this is the future rewards. This is just the rewards times a discounting factor for the subsequent value function. So going from here to here and then recursively defining that, right? We can do the same for the action value again by doing this, but predicated by an extra parameter of the action for the next time step, as well as the current time step when we leave state S. So again, it helps look at some diagrams here. Let's look at the one for V pi, which is our state value function given the policy pi. And here we're at a state, and we have an immediate value that we would like to calculate. And we're going to say, let's look one step ahead. Take a look that we're going to perform this action, and this action is going to give us this Q value, okay? So what can we say from that? Well, we're going to recursively define our value function based on our Q functions, right? And our Q functions, whatever value they return, is going to be explicitly multiplied against the transition probability. But the transition probability that we take this particular action is given by our policy now, not by our state transition matrix, right? So we just look up in our policy, say how likely it is we're going to take this action given this state, okay? And then sum up over all of the cases here, which is going to give our average value, our average Q value over all of the possible actions, and that's going to result in our value function for this policy. Now we can reverse this as well. So if we look at the bottom part of this equation and say, oh, we took a particular action, right? So this particular action from the previous state, we took this and we want to define what this Q pi is, right? So how do we do that? Well, it's going to be the immediate rewards that we're going to get for trying to do that particular action, right? Again, remember that when we look at the MDP as opposed to the MRP, MDPs give perhaps different rewards for taking different actions. That's why we have this A subscript here, okay? But even if we take this action, we don't know exactly what state we'll end up with. For example, think of a cleaning robot trying to go left. In certain situations, it may succeed at going left, or it might bump into an obstacle like a dog or a child, and then end up slightly different than where it wants to go. So the environment gets a chance to react. It tells us which of the states we're actually going to end up in. We might end up on this branch over here, or perhaps on this branch over here, or any number of states that could result from the agent taking this action and the environment reacting to put us somewhere else. So in terms of our instance that we've seen before, when we decided to go clubbing, that was a deterministic decision on the part of the agent, but whether we ended up going back to class 1 or to class 3 depended on the environment stochastically, okay? So how are we going to determine that is basically looking at this part here, which says, for the action that we are taking, we need to know what the state transition probability matrix is, right? So we took an action, but now we're letting our environment decide where we're going to end up. So this is why we've re-indexed our state transition probability matrix with regard to our action as well as our source state and our state that we're going to end up in, okay? This gives us the probability of taking that transition, and then we know what that transition state is worth, because we've already defined it as our state value function given the policy for the new state S prime. Okay, so that's why we have this here. Okay, so again, we have our immediate rewards and our all of our subsequent rewards, right? Future rewards that are discounted. Now, of course, we can stack both diagrams together in either way. So we're going to start to get a first for our state value function. So our state value function is basically saying, I'm starting at a state, I'm going to take an action. That action we can think of as a deterministic action that's decided by us through the policy. It's going to give us to a Q value. This Q value is then calculated through all the different cases that I might get blown to given the environment. Again, whether I'll succeed in going to the intended state, maybe my intended state is S prime, or maybe I end up in a different state based on some stochasticity in the environment. Either way, when I take this particular action, I'm going to associate a reward with it that's conditional on just the action, okay? So I can index that this reward factor, this R, would be the same for all of the different branches that I would go here because I'm taking this particular action from this state here. Right, so we can envision that, right? You can see it here. This part is our subsequent actions, right? And we're getting the reward at this bottom part of the time step. We're just going to, by convention, factor it this way. So we have the top part of the tree, which is just how much our transition matrix is for going to a particular step. And then we have our Q value, which is denoted by this particular term here. Okay. So we can flip it the other way around too, right? We can start from the middle branch where we have a decision that's already made. So this is our action node. And from our action node, we let our environment choose where we're going to go. And then once we are in that state, the subsequent state, we can choose another action. So we can also look at this bipartite tree this way, right? So each level, we're going to have a state followed by an action and a state followed by an action. So you can think of it as interleaved between these parts. Okay, and then the formula for this is also quite straightforward, right? Remember, we have this immediate reward that we're getting for doing this action. That's over here, okay? And then with discounts of the future rewards that we would get aggregated over whatever transition probability we have that's dictated by the environment. That's this part up here, right? The possibility of going to different states, okay? That's indicated through this P superscript A subscript from S to S prime, right? So up somewhere up here we have an S, right? When we've always left from that S, okay? And then what we have over here is then our value function for the subsequent state, right? So this is this branch down here, where we have many of them as predicated by this part here. So all the ones from this summation is the top, and this summation is the bottom one. So how do we verify that? If we're given a diagram with the numbers already calculated, we can check whether this is indeed correct. So let's say, again, we're taking a policy that's not very smart here, taking a uniform policy where we take any of the actions with equal probability, and we can verify. So this 7.4 that we're looking at here, how do we check that? Well, for this case where we're in state free and we have our policy being uniformly decided, we're going to take this arc this study arc with a half probability that's uniform. So we would get an immediate reward of +10 from there, okay? And then otherwise we'd go clubbing, and our clubbing gives us a reward of 1 to go. So that's here, right? This one is here, okay? And then from this action node, this is the only node in this particular network that we're examining, which is stochastic, which our environment reacts differently. So with 40% chance, we get sent back to class 2. That's the one here, right? Class 2. With 40% chance, we're going to end up back in the same class where we started, class 3. And with 20% chance, we regress and we go all the way back to class 1. So that's this case over here. Okay, so we're going to add all of these rewards together and then times that by 2 to get this part. And indeed, when we calculate this all the way through, we arrive and are able to verify this number as 7.4. So just nicely, as you might have suspected, this also has a nice matrix form, right? So we can think of these as column vectors here. So I have a state value function conditioned on the policy, a reward that's conditioned on the policy. This is also a simple column vector. And then I have a state transition matrix, but now predicated on the policy rather than just probabilities given by the environment. And then my value function. So I have v pi on one side and v pi on the other. I can solve for that, collect all the terms. Again, and you're going to see that it has a matrix inverse, and I can solve directly for this.